All right, let's talk about 6.6. So 6.6 is about inverse functions. Loosely speaking, the inverse of a function encodes the steps that we would take to solve the original function for x. Or another way to say that is that an inverse function undoes the original function, in the sense that if you compose a function with its inverse, then you're going to get just x. You're just going to get the identity back out. Okay? So, for example, if f of x is x minus 3, then if we wanted to solve this for x, we would add 3 to both sides, and the function that encodes this is x plus 3. So we would say that f and g are inverses of one another. And to show that, notice that when we compose f of g, right, when we compose f with g, we get f of g of x, right? So that's f of x plus 3. So that means I'm going to look at f, and wherever I see an x, I'm going to replace it with x plus 3. And we're going to get x plus 3 minus 3, which is, of course, just x. And similarly, if we compose the other way around, g of f, g of x is x, or sorry, f of x is x minus 3. Sorry, this should have been a g, so we're going to do g of x minus 3. So we're going to look at g of x, and wherever we see an x, we're going to replace it with x minus 3. So we get x minus 3 plus 3. And sure enough, we get x. So f and g undo each other, right? They undo each other. Okay? So another example of this, and we saw this in 6.3 example 5. So if you want to go back to 6.3 and look at example 5, we looked at these two functions and we composed them, and what we found is that when we composed them, we got x in both cases. Actually, I think we only did one of the compositions, and I don't remember which one it was, but we got x back out. And so f and g are inverses of each other. Okay? So we're going to make that a definition now, right? So let f be a one-to-one function. We define the inverse of f, denoted by f, this little exponent of -1. This is not f to the -1. It's not the same thing as 1 over f, right? We read this thing f inverse. It's an unfortunate notation. I wish that there were a different notation for the inverse, because this makes it seem like you're saying 1 over f, which is not what you're saying, right? We read this f inverse. But the inverse of f, denoted by f to the -1, right, f inverse, is the function such that when you compose the original with the inverse, you just get x back. Or if you compose the inverse with the original, then you get x back for all x in the domain of f. So, let's practice. So we're going to look at a couple functions. We're going to guess what the inverse is. We'll talk about how to find the inverse in a second, but for now I think we can sort of try to develop some intuition and just guess what the inverse is, and then verify that our guess is correct by computing these two compositions. Okay? So for f of x equals 3x plus 2, remember the inverse is the function that's supposed to undo this one. So if you think about solving this for x, first we would subtract 2, and then we would divide by 3. So my guess for f inverse is that I'm going to take some number, subtract 2 from it, and then divide by 3, right? So that's what I'm guessing f inverse is. Now to check, we can compose f of f inverse. This is going to be f of f inverse, right? Or what I'm claiming is f inverse. That's going to be, I'm going to look at f and replace the x with x minus 2 over 3. So that's 3 times x minus 2 over 3 plus 2. That would be x minus 2 plus 2, right? Because the 3's cancel. And then that would just be x because the 2's cancel. And sure enough, right? We have to check the other one too. F inverse of f. I'm going to run out of room though. But this would be f inverse of f of x, 3x plus 2. So I'm going to look at what I'm claiming is f inverse and replace the x with a 3x plus 2. I would get 3x plus 2 minus 2 over 3. The 2's are going to cancel, the 3's are going to cancel, and we're just going to get x again, right? So f inverse of f and f of f inverse are both just x. They're just both the identity. And so that tells us that this is the correct inverse. For part B, maybe it's a little easier. Go ahead and give the video a pause. What would undo this? If you had to solve this for x, how would you do that? Okay, so here's my answer. Here's my guess. I'm going to say f inverse of x, I think, is e to the x. Because if I wanted to solve for x, I would exponentiate by e, right? So I'd say e to the x. And we can check that, right? If we take f of f inverse, this would be f of e to the x. That would be ln of e to the x. The bases match, right? This is a log base e of e to the x, so we just get x, sure enough, right? And if we look at f inverse of f, this is going to be f inverse of ln of x. That's going to be e to the ln of x. Again, the bases match, so they cancel, and you just get x, sure enough. Okay, so this is the conceptual understanding of an inverse, right? An inverse is something that undoes the original function. And we saw this earlier on in the semester when we talked about inverse trig functions, right? Like if we wanted to undo sine, we would take sine inverse of both sides, right? Because sine inverse undoes sine. We'll talk more about the inverse trig functions in the next section. For now, I want to discuss some more things about inverses in general. Okay, so first of all, suppose that f is 1 to 1 and that f of a equals b. If that's the case, you can take f inverse of both sides of this function, right? F of a equals b implies that f inverse of f of a equals f inverse of b. Well, f inverse undoes f, right? So f inverse of f of a is just going to be a. So you're going to get a equals f inverse of b. Similarly, if a equals f inverse of b, you can take f of both sides, and f of f inverse is just going to leave you with b, so you see f of a equals b. So what this means is that f inverse of b equals a if and only if f of a equals b. Okay, that fact has several important consequences. First of all, it tells us that to graph f inverse, all we have to do is switch the coordinates of the points on the graph of f, right? Because if f inverse of b equals a, then that means that the point BA is on the graph of f inverse, right? The point BA is on the graph of f inverse. F of a equals b means that the point AB is on the graph of f. So if AB is on f, then BA is on f inverse, right? We just switch the coordinates around. Number two, it tells us that to find f inverse algebraically, all we have to do is switch x and y and then solve for y. And I'll show you some more of this on the next page. Number three, it tells us that the domain of f is the range of f inverse, and that the range of f is the domain of f inverse. So that's kind of an interesting fact too. Let me give you some examples, right? So number two here says the graph of f is given below, use it to graph f inverse. Okay, so this is actually super easy. We just switch the coordinates around. So this point right here, for example, is the point -2, -1. So -2, -1 is on f. So if we want to know what points are on f inverse, well, we would just switch the coordinates. -1, -2 must be on f inverse, right? 0, 0 is on f. That means that 0, 0 is on f inverse, right? 2, 1 is on f. That means 1, 2. 1, 2 is on f inverse. 3, 3 is on f. Well, that means that 3, 3 is on f inverse. finally 4, 5 is on F. That means that 5, 4 is on F inverse. And what picture do we get if we connect the dots? It looks like that, right? It looks like that. Note the symmetry here, right? F inverse, so this was F, right? And this thing is F inverse. F inverse is just a mirror image of F. F inverse and F are always symmetric with respect to the line y equals x. In other words, they're symmetric about this straight line right here. Right? If you flip them across, or if you fold across that line, the two graphs are going to meet. They're going to match up, right? And that's always true of inverses, right? The inverse function is always it's always symmetric about the line y equals x with the original function. So, so that's kind of a cool thing about inverse functions. Let's see if we can find the inverses of some functions, and we'll make sure to restrict the domain as needed. What I mean by that is we're going to use the fact that the range of f it should be the same thing as the domain of f inverse to make sure that that we're getting the appropriate domain. So I'll show you what I mean. So let's do f of x equals 2 to the 3x plus 1 minus 4. You can think of f of x like y. So what we have is y equals 2 to the 3x plus 1 minus 4. To find the inverse, we just switch x and y and then solve for y. So to find the inverse, we would say, all right, x equals 2 to the 3y plus 1 minus 4. And now let's solve for y. So to solve for y, I would add 4. Then I would take a log base 2. Then subtract 1. And divide by 3. And I'm going to switch sides now and say y equals log base 2 of x plus 4 minus 1 over 3. Right? There's your inverse function, potentially. We just need to make sure that the domain of this function is the same as the range of this function. Okay? So what is the standard domain here? The standard domain would be, well, we would need for x plus 4 to be bigger than 0, so we would need for x to be strictly greater than negative 4. Right? Is that what we get here? Well, yeah, of course, because this is an exponential that's been shifted down 4 units. And so it has this horizontal asymptote at negative 4. And it's going to look something along these lines, right? So the entire function is above negative 4. So the range of this function is negative 4 to infinity. Well, that's the same as the domain of this function, negative 4 to infinity, right? So, so I'm comfortable just saying that this is in fact f inverse. It's log base 2 of x plus 4 minus 1 over 3. There's f inverse of x. No need to restrict the domain on it. The standard domain of this function already matches the range of the original function. So that's perfectly fine. So we don't need to restrict the domain. Let's look at part B. We're going to do the same thing, right? We're going to say x equals cube root y plus 1. And then you're going to solve for y. In this case, in order to undo a cube root, we cube both sides. So we get x cubed equals y plus 1. And then we get y equals x cubed minus 1. Now, I need to make sure that the standard domain of this function matches the range of this function. Now, what's the range of this function? Well, it's a cube root function, shifted left 1. So it looks something like this. So if you think about what the range is, the range of this function, so this is f, right? The range of this function is going to be, well, all real numbers, right? So the standard domain of this function already matches the range of this function, so I don't need to restrict the domain. f inverse of x is just x cubed minus 1. At this point, you might start to be really curious about, like, why am I bothering making sure that the standard domain here matches the range there? Well, you'll see. It doesn't always, and so if it doesn't, then we have to restrict the domain. Part C, I think, is going to be an example of that. So let's do part C. We're going to say x equals square root y minus 2, and then solve for y. So we square both sides, and then add 2. Y equals x squared plus 2. Now, the domain of this function needs to match the range of this function. The standard domain here is all real numbers, but the range here is not all real numbers, right? The range, if we think about graphing square root of f of x equals square root of x minus 2, it's a square root function that's been shifted right 2 units. So it looks something like this, right? Notice that the range is 0 to infinity. That means that the domain of this function needs to be 0 to infinity, not all reals. So when I write down the inverse, I'm going to say the inverse is x squared plus 2, but only for x greater than or equal to 0. Okay? So I need that domain restriction in order for this to be technically correct. And to kind of drive that point home further, what does the x squared plus 2 look like? It's a parabola with a vertex at 0, 2, and so it would look something like this. Okay? Now, inverse functions are supposed to be symmetric with respect to the line y equals x, right? We saw this on a couple pages back. But if you fold these two functions across this line, this part of the function, this part of the inverse, matches up with this original function. But this part should not be there, right? It shouldn't be there. In order for you to have that symmetry, this shouldn't be there. So that tells you that your inverse function, f inverse, needs to be x squared plus 2, but only the right-hand side of it, not the left-hand side. It only needs to be the right-hand side. Okay? And so that's why we make the restriction, right? We're only taking the right half of the parabola, not the whole thing, as our inverse. Okay? Let's do part D. This is going to go really similar. We're going to say x equals negative square root y minus 2. We square both sides, and we end up with the same function as we got in the previous example, y equals x squared plus 2, right? Y equals x squared plus 2. The difference is that here we're going to take only part, we're only going to take probably the left-hand part. Let's see. If we graph the original function f, it's a square root function that's been shifted right 2 units and reflected, so that instead of opening up this way, it's going to go down this way. So now if you think about the range here, the range is negative infinity to 0. So that means the domain of our inverse function needs to be at negative infinity to 0. It needs to be everything less than or equal to 0. So there's the actual inverse. And again, we can see that if we graph this parabola, it would be a parabola with vertex 0, 2. But I'm saying here I only need to graph the left-hand side of it, right? The stuff when x is less than or equal to 0. And that makes sense, right? If you fold this across that y equals x, then the two edges are going to match up. That wouldn't happen if I had the right-hand branch on it, right? So I don't need the right-hand branch. I only need the left-hand side. Okay? So this is an example where you get the same rule, x squared plus 2, but the function is different because here you're taking the right hand and here you're taking the left hand. Okay? So that's why it's important for us to always think about what's the domain of our inverse function, and does it match with the range of our original function? If not, then we need to do some kind of restriction. Two more. Okay, these are kind of interesting. So let's do it. We've got x equals y over y plus 3, and we need to solve for y. Well, in order to do that, I need to clear denominators. So I'm going to multiply both sides by y plus 3. I get x times y plus 3 equals y. Now, it's been my experience that students will sometimes stop here and circle their answer with glee. They're like, oh, I found the inverse. I've solved for y. Well, it's true that you have a y by itself on the right-hand side, but you haven't solved for y because, well, you have another y on the left-hand side, and you need to get these y's together, right? So here's how we're going to accomplish that. Let's distribute the x. And then I'm going to get all of my y's on the same side of the equation, and all of anything that doesn't have a y on it, I'm going to put on the other side of the equation. So I'm going to move this y over here, get xy minus y. I'm going to move this 3x over there and get negative 3x. Okay? Now I can factor out a y. And then I can divide by x minus 1 to get y equals negative 3x over x minus 1. Okay. Now, I need the domain of this function to match the range of this function, of my original function. Okay. Well, what's the domain of this function? It's going to be all reals except for 1, right? Because 1 makes the denominator 0. So it's going to be all reals except for 1. Well, what's the range of this original function? That's a little bit harder to tell. We would have to do some work maybe to graph it to see what the range is going to be. If we do some long division, so x divided by x plus 3, this goes in once with a negative 3 left over. So really f of x is 1 minus 3 over x plus 3, or better yet, we could call it negative 3 over x plus 3 plus 1. So what's that going to look like? So it's going to look like 1 over x, except that it's been shifted right 3, or left 3, and up 1. So I'm going to have an asymptote there, up 1, and have an asymptote there. And then it's been flipped over and stretched by a factor of 3. Well, so usually it looks like this and this, but since it's been flipped over horizontally, right, because of that negative right there, it's actually going to look like this and like this. Okay, it really doesn't matter all that much. What we really want is to know what the range of the function is. Well, the range of the function is going to be negative infinity to 1, and then 1 to infinity. The only value not in the range is 1 itself. Well, that matches with the domain of the original function, right? So there's no need to do any domain restriction here. F inverse of x is indeed going to be negative 3x over x minus 1, just with its standard domain. So no need to write down any restrictions. Okay, let's do another one kind of like that. This will be our last example. So again, we're going to switch x and y, and then solve for y. So I'm going to clear the fraction. And I'm going to get my y's together and my non-y's together. Then I can factor out a y. And then divide through by x minus 1. You know, I just realized something. In the previous problem, we know that the range is going to be all reals except where you have a horizontal asymptote, right? Well, the degree of the numerator matches the degree of the denominator, so you have a horizontal asymptote at 1. So I could have avoided, I didn't actually have to even graph it. I could have just realized, well, I'm going to have a horizontal asymptote at 1, so the range is going to be all real numbers except for 1. which matches with the standard domain. So I'm going to do that same trick up here, and rather than try to graph this original function, I'm just going to realize I should have a horizontal asymptote at 1. Okay, so I should have a horizontal asymptote at 1. That means the range is going to be all reals except for 1. Well, the range of the original function is all reals except for 1. Well, what's the domain of the inverse? What's the standard domain here? Well, it's all reals except for 1. Well, so there you go, right? So no need to restrict the domain any further. F inverse is 7x plus 3 over x minus 1. And that's all there is to it. Okay? So that's all I have to say about inverse functions for now. In 6.7, we're going to talk about inverse functions of non-injective functions. So inverses of non-injective functions. And the reason is because in this section we've talked about, when we gave our definition, we said f had to be 1-to-1, right? So what happens if you have a function that's not 1-to-1? Can you still have inverses? You know, what does that mean and all of that? So we'll talk about that in the next section.